welcome to Lab 3. The purpose of this lab is divided into two parts. The first part is to analyze the star's motion to find the net force on the star for all points in the dataset. The second part is to fly around the black hole without crashing into the planet or the black hole. The computational model was GlowScript. Some physical principles that I used was the force perpendicular equations and the force parallel equations. I used the velocity and update formulas and Newton's law of gravitation. So the mass of the black hole I calculated was this, and the initial velocity in part 2, in the x direction it was negative, and the y direction it was this. So physics principles. So the top equation right here is a parallel force, and the next one is a perpendicular force, and those added together equal the net force, and uh, so this is Newton's law of gravitation right here, and then I use the velocity and position updates as well. So the perpendicular force was used to get the centripetal force. I calculated the net force with the change in momentum over time. I used F parallel equals the net force minus the force perpendicular to get the force of parallel. And then I used the net force in Newton's gravitation equation to get the mass of the black hole. And then I used the velocity and position update to get the path of the starship. So system surroundings plus initial conditions. Part 1, the system was a star. The surrounding was black hole. The initial conditions, I changed the mass of the star plus the delta T. And part 2, the system was a starship. The surrounding was a black hole plus the planet. Initial conditions, I guess and check the initial velocity of the ship, and then I got the black hole mass that I calculated in part 1, and the planet and the star in the ship. So part 1. So yeah, I changed the star's mass to what it was in the instructions, and then I calculated the time in a day. Yeah, so I got the momentum initial and the momentum final using the equations that I said earlier, and then the delta V and the delta P is just the final minus initial, and then delta P over delta T is the force. And then so when you do the unit vector of the momentum, and then you get the magnitude of delta P over delta T, you get the force perpendicular, and then the force perpendicular equals the dp dt perpendicular, and then right here the force parallel equals the net force minus the net force perpendicular, and then using the gravitational equation, I get the mass of the black hole. And then so when I run this, you can see that the orange line is the net force, the purple one was the perpendicular, and the blue one was the parallel. And then this is the mass of the black hole right here that I averaged. And then I use that in part 2 to set the black hole mass equal to that. And then I changed the timestamp, and then this is the speed right here. And then these were my equations that I used to get the update of the ship. So when we run this, you can see that the purple line indicates where the starship is, the path of the starship, and the blue line is the path of the planet. So similarities and differences and possible errors. This is a computational model. There's nothing compared to in real life. I haven't been to space. This is not how the universe works. Like, ships cannot travel like 10% the speed of light yet, and black holes are also moving in real life. There can't be possible errors because this is all based on theory and formulas. So what does this mean? So the rate of change of momentum is the net force. As a result, the net force's parallel and perpendicular components are equal to the change in momentum's parallel and perpendicular components. They would be equal. So now if to get the ship in an orbit around the black hole, I need to change the velocity to that. And so 9e5, and then 9, 6. Yeah, so when we run this, the blue line is a planet, and then the purple line is the ship. So hope you enjoyed my presentation. Like and subscribe the video.